Eris should be dead. By every rule of planetary science, it should be a frozen corpse, so distant that sunlight takes 13 hours just to reach its surface. Temperature locked at around -240 degrees Celsius. No star close enough to warm it. No companion planet to pull and flex its interior. Eris has spent billions of years at the outer edge of our solar system, and the assumption was always that it spent that time doing exactly nothing. A relic. A leftover. Then on August 30th, 2022, James Webb pointed one of its most sensitive instruments at this world. What it found was not what a dead world should look like. That is where the story begins. Eris was discovered in 2005 by a team at Palomar Observatory: Mike Brown, Chad Trujillo, David Rabinowitz. It was the discovery that broke the solar system. Not because the object itself was so strange, but because it was roughly the same size as Pluto. And that created a problem. If Pluto was a planet, then Eris was a planet. If Eris was a planet, there might be dozens more waiting to be found. The International Astronomical Union could not call everything a planet. So instead, in 2006, they redrew the rules and reclassified Pluto as a dwarf planet, and Eris along with it. They named the new object after the Greek goddess of discord. It fit. Even its discovery caused a fight. Eris lives in a region called the Scattered Disk, a chaotic gravitational frontier beyond the Kuiper Belt, from which Neptune's gravity ejected it billions of years ago. Its orbit is extreme, an ellipse so stretched that over its 560-year journey around the Sun, it swings from roughly 38 astronomical units at its closest to nearly 97 at its farthest. Right now, it is near the outer end of that arc. The Sun from its surface would be a bright star, barely distinguishable from the background. Cold, dark, remote, a world that should be nothing more than an ancient ice ball, preserved in the silence of deep space. That was the model. Now look at the surface. Eris reflects approximately 96% of the sunlight that reaches it. That albedo, a measure of reflectivity, makes it the second most reflective body in the entire solar system. Only one object ranks higher: Enceladus, the small moon of Saturn. And Enceladus is not reflective by accident. Enceladus has an interior ocean. Liquid water under pressure pushes through cracks in its icy crust, jets into space, and falls back as fresh white snow. It is continuously repainting itself. That is why it is so bright. The surface is never old. Eris is equally bright. That comparison is not decorative. It is the alarm. The simplest version of the story, version 1, says the brightness is nothing more than a natural consequence of Eris's eccentric orbit. As it swings slightly closer to the Sun during its 560-year cycle, trace gases on its surface sublime, rise briefly as atmosphere, then freeze back down as the world moves away again. A frost cycle, self-renewing, cold, mechanical, ancient. No interior activity required. Eris is just a frozen relic with a very efficient surface process. That should be enough. It almost is. But then Webb looked closer. On August 30th, 2022, the James Webb Space Telescope's Near-Infrared Spectrograph, NIRSpec, observed Eris for the first time at wavelengths spanning 1 to 5 microns. The instrument was cooled to -233 degrees Celsius to detect faint infrared signals from a target 95 astronomical units away, more than 14 billion kilometers. The light that entered Webb's detectors had been traveling for 13 hours before it reached the telescope, and inside that light was a chemical message from Eris's surface, more detailed than anything captured before. The first confirmation was expected: methane ice, rich, and abundant. Eris had been known to have methane since early spectroscopic surveys. No surprise there. But then the data revealed something no instrument had ever seen before on a trans-Neptunian object: a specific isotope of methane, monodeuterated methane, written as CH3D. Methane with one hydrogen atom replaced by its heavier cousin, deuterium. And with that, detection came a number: the ratio of deuterium to hydrogen in Eris's methane, 2.5 plus or minus 0.5 times 10 to the minus 4. That number is a fingerprint. Chemistry is forensic in this way. The isotopic ratio of a molecule preserves information about the temperature and environment where it was created, not where it happens to sit now. The chemistry remembers, and what this number remembered did not match the cold. Primordial methane, the kind inherited from the protoplanetary disk where the solar system formed, has a different isotopic signature. Models of what that disk looked like, combined with measurements of comets and other preserved relics, give a clear prediction of what primordial methane's deuterium-to-hydrogen ratio should look like. Eris's methane does not match that prediction. The geochemical analysis, published in Eris in early 2024 by Christopher Glein and colleagues at the Southwest Research Institute, was direct. Primordial methane, as currently understood, is inconsistent with what Webb measured. The methane on Eris was not born in the cold. Then came the second piece. Carbon monoxide was not there. No detection at 4.67 microns, where it should have appeared clearly. That absence is significant because carbon monoxide and methane form together in the cold chemistry of the protoplanetary disk. They are partners. You find primordial methane, you expect primordial carbon monoxide. Eris has one without the other. The methane's chemical partner is missing. The simplest version, frost cycle, ancient relic, nothing unusual, cannot explain that. Version 1 gets you to the surface. It does not get you past the spectrum. Here is what the leading alternative says. Eris has a rocky, differentiated interior, a dense core of rock and silicate minerals, confirmed indirectly by its bulk density of approximately 2,400 kilograms per cubic meter. That density is not what you get from a snowball. It is the density of a world with rock inside. And rock, in the early solar system, contains radioactive elements: uranium, thorium, potassium. These decay, they release heat. Over the first billion years of Eris's existence, that radiogenic heat could have raised the temperature in its core to above 150 degrees Celsius, hot enough to drive chemistry between rock, water, and carbon dioxide. Hot enough to produce abiotic methane through hydrothermal reactions at a rock-water boundary. That methane would have migrated outward through the interior, eventually reaching the surface and freezing. The surface you see today would be the product of that internal chemistry, not the original inheritance from the disk. That is version 2, and it explains the DH ratio. The geochemical models developed by Glein and colleagues show that both abiotic hydrothermal methane and thermogenic methane, produced when radioactive heat cooks complex organic molecules, can produce DH ratios that overlap with what Webb measured. The chemistry fits, the numbers fit. But version 2 has a problem it cannot resolve quietly. If the interior was hot enough for that chemistry to occur, and if that chemistry required liquid water as a medium, then at some point, possibly for billions of years, Eris had liquid water inside it. A world at 96 astronomical units from the Sun, in near total darkness, could have harbored a subsurface ocean. The heat that drove the methane chemistry and the water that enabled it are the same conditions that scientists identify as the prerequisites for complex prebiotic chemistry on Earth. That does not mean anything lived inside Eris. The data does not say that, but it means the question is no longer as simple as frozen relic at the edge of the solar system. The heat source is radioactive decay. That much is plausible. But radioactive decay fades over time. The elements run out, the heat diminishes. After 4.5 billion years, most of that energy should be gone. Which brings the problem back around to the surface. The albedo is still 0.96. If the methane was produced billions of years ago, when the interior was still warm and the heat has since faded, why is the ice still fresh? Methane exposed to solar radiation and cosmic rays darkens over time. It weathers. Makemake, a similar dwarf planet that Webb also observed, shows a redder, dimmer surface, exactly what radiation weathering produces. Makemake's methane is aging. Eris's is not. The surface looks young. Enceladus looks young for a specific reason. What is Eris's reason? That question is still open. And the albedo, still sitting at 0.96, has no clean answer from either version yet proposed. The most useful comparison in this story is not a distant galaxy or a black hole. It is a moon of Saturn, 1.4 billion kilometers from Earth, roughly the size of the United Kingdom. Enceladus has a confirmed interior ocean, liquid water under an ice shell, kept warm by tidal forces from Saturn's gravity. That ocean pushes upward through fractures near the moon's south pole, erupting into space as plumes of water vapor and ice crystals. Cassini flew through those plumes. It tasted them. The chemistry was there. Organic molecules, salts, silica grains that could only form at hydrothermal vents on the ocean floor. Enceladus is one of the most scientifically compelling objects in the solar system precisely because everything about it suggests the conditions for chemistry more complex than anything we have yet confirmed. Now hold that image and look at Eris. No plumes detected, no flyby data, no Cassini equivalent that ever came close. The entire scientific record of Eris consists of spectroscopic measurements taken from telescopes that never left the inner solar system. Webb's observation in 2022 was made from 1.5 million kilometers above Earth, a telescope reading the faint infrared breath of a world 95 astronomical units away. And yet, the surface brightness of that world matches Enceladus, a moon we know is alive, a moon we know is actively resurfacing itself. The only body that shares Eris's reflectivity also happens to be one of the most geologically dynamic objects we have ever studied. That comparison is still the alarm. It has not gone away. Here is where the story gets genuinely complicated, because the science is not settled. A 2025 paper published in the astrophysical journal Letters, Mouses and colleagues, argues that the D per H ratio measured by Webb may not require an internal origin at all. The math, they suggest, is also consistent with methane that was inherited primordially from the protoplanetary disk if specific conditions in that disk are assumed. CO's absence, under this interpretation, can be explained by it being destroyed through reactions in a subsurface water layer, or by depletion at methane's ice line during the disk's formation. The primordial explanation, this team argues, should not yet be ruled out. That paper is real. It is peer-reviewed. It is a legitimate counter-interpretation, not a fringe objection. And its existence matters, not because it weakens the story, but because it makes the story honest. The measurement is settled. The interpretation is not. Two teams, two models, one dataset, and the gap between them is still wide enough to contain a genuinely different kind of solar system. But here is what the primordial counter-model cannot explain without additional assumptions stacked on top of each other. The albedo, the freshness of the ice, the fact that Makemake, a world with similar size, similar composition, similar distance, has a redder, dimmer, radiation-aged surface, while Eris remains almost mirror-bright. If both worlds inherited their methane primordially, and both have been sitting in the same radiation environment for the same 4.5 billion years, why does one look ancient and the other look new? Radiation does not play favorites. Time does not either. Eris's surface is behaving like something that is being refreshed. The primordial model does not easily produce that behavior. Version 2, the internal heat model, remains the leading interpretation among the scientists who led the Webb analysis. The logic is this. The rocky core of Eris underwent substantial radiogenic heating in its early history. The heat drove hydrothermal chemistry at the boundary between rock and water. That chemistry produced abiotic methane, not from living things, not from the primordial nebula, but from the reaction of carbon-bearing compounds with water and rock at elevated temperatures. The methane migrated outward. It reached the surface and froze. The surface is not a relic of the solar system's birth. It is a product of Eris's own interior. That is a cleaner explanation. It accounts for the DH ratio, the absence of CO, and the density of the object. It is the version the published geochemical models support. And it is still not the most disturbing part of the picture. The disturbing part is what the internal model requires. If methane was produced at temperatures above 150 degrees Celsius inside a world with a bulk density of 2,400 kilograms per cubic meter, a density consistent with a significant rock fraction, then the process that produced it almost certainly occurred in the presence of liquid water. Rock plus heat plus water is the geometry of hydrothermal chemistry. It is also the geometry of the deep ocean vents on Earth, where the earliest evidence of biological chemistry is found. That is not a coincidence being exploited for drama. It is a genuine overlap in the physical conditions. The same temperatures, the same pressures, the same chemical reactants, these are what scientists identify as prerequisites for prebiotic chemistry. The data says those conditions plausibly existed inside Eris. For how long is unknown. Whether anything more complex than methane resulted is a question the data cannot currently approach. What the data can say is this. A world nearly 100 astronomical units from the Sun, in darkness so complete that the Sun appears as nothing more than an unusually bright star, may have had a warm, wet, chemically active interior. The cold outer solar system is not what the textbook said it was. Planetary scientist Bonnie Berati of JPL said it directly in the scientific press. Methane would have to be constantly produced in the interior to explain the isotopic ratios Webb measured. Constantly. Not billions of years ago and done. Not a one-time event preserved in ancient ice. Continuously. If that interpretation is correct, something is still happening inside Eris right now. The heat has not fully faded. The chemistry has not stopped. That is not confirmed. It is inference from a surface that will not age. But the inference has not been closed off by any measurement yet taken. Think for a moment about what this observation actually was. No human spacecraft has ever visited Eris. No probe has been funded. No flyby has been approved. The most detailed measurement ever made of this object was performed by a single spectrograph aboard a telescope orbiting the Sun 1.5 million kilometers from Earth, capturing infrared light that had traveled 14 billion kilometers before entering the detector. The scientists who interpreted those signals built geochemical models, mathematical reconstructions of what must be happening inside a world they have never seen up close, based on the ratio of two isotopes in light reflected from a surface they can only infer. The measurement is real. The instrument is the most capable of its kind ever built. But the gap between what Webb can see and what Eris actually contains is enormous, and it is still filled largely with inference, modeling, and the careful language of scientists who know the difference between what the data shows and what it suggests. That gap is not a failure. It is the current boundary of human knowledge about a world that has been sitting at the edge of the solar system for 4.5 billion years, apparently unimpressed by our attention. Eris should be dead. That was the premise. A frozen relic, preserved in the dark, unchanged since the solar system's formation. The textbook version of an outer solar system object. Cold, quiet, geologically inert, chemically ancient. The textbook was not wrong about what such a world should look like. It was wrong about Eris. Dead worlds do not have fresh surfaces. Dead worlds do not produce methane that requires temperatures above 150 degrees Celsius to explain. Dead worlds do not resemble, in the one measurement that most directly reflects geological youth, a moon that we know is actively venting liquid water into space. Eris's next closest approach to the Sun, its perihelion, will occur in the year 2257. Every person alive on Earth today will be gone by then. Their children will be gone. Their grandchildren may be gone. Eris will still be moving along its 560-year arc, white and silent, carrying a surface that does not age the way it should, holding an interior that no instrument yet built can fully read. The Webb data will still be the best measurement humanity has of what is happening inside it. Whether the heat source has finally faded by then, or whether Eris is still quietly producing something beneath that mirror-bright crust, the data as it exists today cannot say. That is not a gap in the story. That is the story. A world named after discord, sitting at the outer edge of the solar system, refusing to behave like something dead. Still white, still bright, still carrying the chemical signature of heat and water in a place where, by every prior assumption, there should be neither.